Okay. All right. It's told me that recording has started, so hopefully that is true. Um, so I guess hi everybody. Welcome back. This is the last workshop that we will have, and that you will have probably ever. Which, hey, that's kind of good, right? I mean, I guess it's sad because you can't spend your Sundays learning organic chemistry anymore, but at the same time, you won't be spending your Sundays learning organic chemistry anymore. So, uh, most likely most of you are pretty happy about that, which I could totally agree with. Um, but now is a good time to sort of like take this workshop to look back at some of the bigger themes and the ideas that you've learned throughout this class. Like, uh, now that you know all of it, you can look back um, with like the perspective that you've gained because you've seen it. Um, so yeah, okay. Anyway, how about we just start going through it? Okay. I'm going to sort of talk about some of the big themes that you've talked about in this class. Um, Not necessarily in the order that you've learned them, because the book is sort of structured based on, like, oh, look, here's what you can do with ethers, here's what you can do with ketones, and then here's what you could do with carboxylic acids or whatever. Which, like, it's good to keep track of the reactions, but it's not very like it doesn't it makes it harder to see what the common themes are between all the things that you've learned. So I'll actually start off with saying that the most important thing that you've learned is probably reactions using carbonyls. Okay, so carbonyl reactions. Um, if there's like one thing that you could say this class is about, it's carbonyls because they're just one of the most useful and versatile functional groups. Um, they're super important because they put polarization onto a carbon, and they're also withdrawing groups. That gives us a couple of effects, right? You can attack at a carbonyl, which you started to see in Orgo 1, um, but you use it a lot in this class as well. And then they're also withdrawing groups, which is super important for reactions with aromatics, like you could do Friedel-Crafts, using the fact that carbonyls are um, they're polarized. Yeah, there we go. Uh, so you could do stuff like that, and you could also use the fact that they're withdrawing to do like um, the most recent stuff you learned. I'm totally blanking. Okay, yeah, the alpha keto making enolates. There we go. So you can use them to do that too, and that uses the property that they're withdrawing, which is like a really big thing. Um, so in terms of these, you've learned like a few major things. So there was this period in like the middle of the course where you kind of focused on the reactivity series of them. Okay. Um, so that was like you have these sort of you have acid chloride, and then you have anhydride, and then there's thioethers over here, which they're neat, but we don't talk about them that much. So you have these anhydride, uh, and then going down from there, you have let's see what like I think amide, ester, and then an acid. Yeah, hopefully that's the right order. Um, so we have this, and then there's a whole like there's a whole bunch of ways to convert between them and go back and forth. Probably the most important is that you can go up using SOCl2. That's like really good because it kind of lets you reset. It lets you go back up to the top, and you know you can go from the top down to anywhere. So that's kind of useful and helpful. But you didn't just learn about these in terms of the reactivity series. I mean, you did, and this is super useful. And there were like 3 chapters about this where you just had to kind of remember a lot of the different conditions that you can use to go from one to another. But you learned some other stuff about them too, which is also useful and important. So there was a large section about these sort of alpha keto reactions. Um, yeah, I think the textbook uses some name to classify them. Whatever that was, I don't remember. But you can use these reactions where you make enolates. So this like is pretty dependent on the keto enol tautomerization. Um, and there's so much that you could do with these, right? You can use them to uh, make carbon-carbon bonds, which is sort of like for a while the only way you knew how to do that was using Grignard reagents or some sort of organometallic. But now you could do that in a really flexible way, and in a fairly easy way because you just have to put them in acid or base, and they will combine, they'll condense. You can also use it with like esters in order to make some beta keto ketones or uh, beta keto alcohols. Um, and then there's other like cool stuff too, right? You could do like the Michael addition, which you learn towards the end, which is a useful way of um, using these reactions to do some kind of like complicated and longer chain things. There's also another reaction which maybe uh, you haven't thought about in a while because it's kind of been a while ago, and the textbook doesn't focus on it that much, despite the fact that it's such a powerful reaction. And I kind of talked about this like while we were still on campus, but you also learned about the Wittig reaction. Okay. So if you remember, that's letting you take like a carbonyl and then you take some Wittig reagent, and then that lets you just make a double bond onto that thing like that, which is oh, actually, I drew my Wittig reagent a little bit wrong. Oh, where's my eraser? Sorry, my eraser is normally over here. But here we go. So, uh, so it lets you do something like that, which is super useful because hey, look, you can well, I guess you can actually have something else over here too, right? Some other R group. Because it lets you just take a carbonyl and swap out the oxygen with something else that you want. I was going to say whatever you want, but uh, you might have to be a little bit more careful with that because it's not like totally that lenient. But it lets you, make this double bond, and that is unexpectedly powerful. Um, and I would keep this reaction in mind, definitely. Okay. All right. Well, anyway, you spent a whole bunch of time talking about these ketones and stuff that they could do, um, which is really useful and sort of related. I'm trying to hit on the big themes, so I'm trying to like have some sort of connection, some sort of transitions between them, but uh, it's not totally like some of them are a bit of a stretch. Anyway, uh, so you have a lot of these carbonyl reactions, and then we talked about these alpha keto reactions. So a good number of these alpha keto reactions are kind of used in these cyclization reactions. Okay. So that would be You could do some of them with carbonyls. So a lot of them are carbonyl related. Okay, that would be like you could do esterification, especially Fischer esterification to make cyclic esters, which are called lactones. You could do esterification. You could do like there was like the Dieckmann condensation, which is like Claisen, but you're just using it to do cyclization. You also have probably done like countlessly many Robinson annulations, which are just Michael additions followed by uh, dehydration reactions. Okay, and then there are probably others maybe that I'm missing, uh, but you've seen a good number of ways to make things cyclic, which you kind of started to get in Orgo 1 because there were a whole bunch of different ways to do intramolecular reactions. That's where you started to see those come in. Well, here you have some more intramolecular reactions that you could do, um, and that will get you cyclized things. But maybe the more important reason why I brought up this whole cyclization thing is because you also learn another very important cyclization reaction, which is Diels-Alder. And really, this whole category is dedicated to Diels-Alder. Like that's the real reason that I brought it in. It's really pretty unlike any other reaction that you learn in this class or the class before. So it kind of deserves its own section. Um, there are like a good number of rules for this. So you have like the endo rule is something that you had to deal with. Um, you also had like products being either 1,2 or 1,4, which had to do with the um, charge localization. So like which end tends to be positive and which end tends to be negative of your diene and your dienophile. So remember, these had to do with diene and dienophile. Okay. So that like what sort of regiochemistry your product takes on has to do with like the which side is positive and which is negative, the diene and dienophile. And then you had this endo rule to deal with too, so there was a huge amount of stereochemistry. Um, and then you get really complicated stuff like if you take uh, something that looks like this, and then you add just this thing or whatever, um, this ethene, and then you get like these really complicated structures, if you remember, right? The double bond moves onto here, and then you get that whole thing, right? And now you have this bridged, like what, bridged bicyclic structure or something. Um, and anyway, this would get complicated. So this really like is a reaction that's pretty unlike the other ones that you've learned. Um, you can use it to make some really specific products, and well, it's pretty important. There's also some good amount to say about like uh, you also learned with this about like the idea of the HOMO and LUMO. Okay, and so you have like reactions that are you have like electrons that are in the HOMO of one of these two reacting with the LUMO of the other. Exactly which is they have to think about it, but um, you saw these two concepts coming up about sort of how electrons move in the reaction and where orbitals overlap. And this was kind of an important concept. So uh, I could very well see there being questions that are like, which of these molecules has the lowest LUMO, for example? Which would have you think about like, okay, which of these reactants would do Diels-Alder reactions the best? Um, So, you'd have to sort of think about something like that. Like, yeah, I think the LUMO goes on to this one. Yeah, goes on to the diene, and then you want to think about like the diene takes withdrawing substituent, so you'd want to think about which one has the most withdrawing substituent, something like that. Okay. Anyway, this is sort of like a big concept. You don't see this very much elsewhere in the course, but it is pretty important, and it is a big concept, especially because this where the HOMO and LUMO are in terms of energy levels depends on withdrawing and donating substituents, which you've really talked about a lot. Maybe I should have included that as a theme. I didn't quite think about that, but uh, well, whatever. Okay, so yeah, you saw these sort of cyclization reactions, and from there we kind of went on and did something that in Orgo 1 you definitely didn't do, which is that we finally got to play with aromatics. So now this is about aromatics and their reactions. Okay, and here there were a few major concepts. So you learned how to tell whether something's aromatic or not, right? First off, because like the idea of what it means for something to be aromatic wasn't really well defined before. Earlier it was just like, okay, here's a phenyl ring that's aromatic. But now you actually learned a way of telling it. Okay, so there's this Huckel's rule, and that says that if there's 4n plus 2 electrons, then it's aromatic. If there's 4n, then it's anti-aromatic. And things that are anti-aromatic will be really unstable, or they'll do anything in their power, like they'll bend, they'll move around, they'll do whatever, in order to not be anti-aromatic, because that's so unstable. But this also depends on the molecule being flat, and also everything being sp2 hybridized. Okay. So you want this, and then you want that. All right. And you could use this to tell about when things are aromatic or not. I think maybe for a brief moment you talked about this sort of like frost circle, which is like if you have a 7-carbon ring or something like that, then there we go. Then you could draw something that looks like this, and I think you draw a line like across halfway down, right? And then those are your energy levels, right? So you fill in electrons as you go, where these are like your bonding orbitals, and these are your anti-bonding. I'm not sure if you focus too much on this. I don't think they really expect you to be able to draw these energy levels, but this is the whole idea behind it, right? For example, this diagram is why this structure that has 7 carbons, yes, it has 7 carbons and 6 electrons, so it's positive like that. It's aromatic. Okay, so this is like an ion that you saw at some point in the course, where if you have a 7-carbon ring where everything is sp2 and there's a positive charge, then this is actually aromatic because it has 4 times 1 plus 2 electrons. All right, anyway, so you saw this Huckel's rule. Okay, neat, right? You had like a million problems classified if this is aromatic, non-aromatic, or anti-aromatic. Really common. But then the other major kind of big concept is that you can actually start doing reactions on them, and you do it using this sigma complex. Okay, so you can use this idea of the sigma complex to do electrophilic substitutions, and you could also use it to do nucleophilic aromatic substitutions, but really only when it's activated. Okay. So when I say activated here, I mean lots of withdrawing substituent. And in electrophilic aromatic substitution, um, activating means donating substituents, right? So the way just to like go back and think about how you approach this is I like to think about it as what is pushing electrons into the ring or what is pulling electrons into the ring. And are you trying to well, yeah, right. So for example, for electrophilic aromatic substitution, um, let's say you have your ring and you have like an amine on it. Okay. So this is a donating group here. So electrons are going to be pushing into the ring. So because electrons are pushing into the ring, they will easily go to something that's electrophilic. Okay. Because, this NH2 is really trying to push electrons down into the ring, and so those electrons need somewhere to go, so they go to an electrophile. That's certainly not how the mechanism works, but it's a good way to think about, like, why this sort of donating group um, will make reactions happen better. Okay. And so you get either ortho or para um, substitution, right? And for nucleophilic aromatic substitution, then if you have uh, this NH2, this NH2 is pushing electrons into the ring, but you also have a nucleophile that's trying to push electrons into the ring, which kind of counteracts what that NH2 is doing, right? You don't want to have two things going in opposite directions. So this isn't really going to work. This is deactivating. Yeah, so that's sort of the big idea with donating and withdrawing groups. And when you look at the actual sigma complex that you're forming, you can try to determine uh, what reactions will happen in things other than just benzene. In benzene, we know that, okay, a donating group will lead to ortho and para substituents. Like, that one we know because you could do it once and it's going to be the same way for every donating or withdrawing substituent. But let's say you go to like pyridine, which has a nitrogen in the ring. Okay, then it's going to be a little bit more complicated, right? Because now you have something that's inside of the ring, and you look at where the charges go around then. Well, yeah. So you could do this whole sigma complex to do every electrophilic aromatic substitution reaction. Okay, that's good. And you can use it to do activated nucleophilic aromatic substitution. But you could also do unactivated nucleophilic aromatic substitution, and that uses this whole benzyne mechanism. Okay. When I first learned about benzyne, I thought it was like a load of garbage. Like, there's no way that, like, it's totally ridiculous that you can have something that looks like this. Like, this is nonsense. It doesn't make sense. But well, I guess it happens. I've tried looking into it before, and people online were pretty much like, "Yeah, it's real. Like, get over it." So you can use this to do when there's nothing on the ring, right? So you could just like take this, and then if you put it in sodium amide, and you will wind up getting aniline like that. This is not a good reaction. Uh, it's going to be way harder to do than if you just do it with electrophilic aromatic substitution. But okay, well, it can be done. Um, you just need super strong conditions, way stronger than you would normally want. So there's a reason why this method is preferred, because you go through a sigma complex like normal. You don't have to go with this whole benzyne thing. But this is another mechanism that you can do. Uh, it is useful, and it can show up. So it is fairly important. All right. There are two more sort of broad concepts that I wanted to talk about. And this one I can't even like try to make it very related to one of the other concepts, because it's just a new class of reactions. You learned how to work with amines, which these, along with carbonyls, are what make organic chemistry actually interesting. Um, and you haven't seen a whole ton of ways to do like proper organic reactions with amines. Besides, earlier you had learned about SN2 reactions, which, okay, most of the, or so SN2, or uh like attacking on nucleophilic attack onto carbonyls. Well, okay. Uh, SN2, that one you learned in Orgo 1, so not a big deal. Nucleophilic carbonyl attack, I mean, you kind of also saw that one in Orgo 1. That's not a super new thing. In this class, you're kind of expected to really like know how to use those with amines, but that's not too crazy, right? An amine has a lone pair. That lone pair is usually pretty nucleophilic, so okay, you can do both of these reactions just knowing it's a nucleophile using kind of old techniques. The more sort of relevant or interesting parts that you've learned now are you learned how to actually synthesize these. That is sort of the interesting part. Okay. Um, One of the biggest ways that you did learn how to do that is by reductive amination. And maybe this is sort of a connection to earlier, because like, hey, reductive amination is entirely dependent on these carbonyl reactions. Okay. You need a carbonyl there, and you have that the nitrogen of whatever you're trying to add attacking into the carbonyl, and you wind up forming an imine. Okay. So to do this in the first place, you need carbonyls. All right. Well, you have reductive amination, so that's kind of a big way. You also have acylation reduction, and this forms an amide intermediate. Like you form an amide, and then you just reduce that amide. Um, so you can reduce using what, two ways? So you can use a lithium aluminum hydride, or you could use Wolff-Kishner as your way of doing it. And then let's see. Yeah, I think you should be able to use Wolff-Kishner, right? Yeah, and then you get an amine. Great. There's a couple of other ways that you can do stuff like this. So there's also like the Gabriel synthesis that we've seen a few times. Like, okay, kind of, it's interesting. It is useful, but it's kind of specific, right? You can only use it to make like primary amines. You can't go too crazy with it, so not too worried about it. And then you also learned how to do some new reactions. And really, the ones that you learned are two different elimination reactions. So you learned Hoffman elimination, and you learned the Cope elimination. Okay. And these two have like, their own different specificities. They have their own different like idiosyncrasies that you have to think about. But these are kind of the main two reactions that you've really learned that aren't just dependent on doing SN2 or attacking a carbonyl with your nitrogen. Um, these are sort of like the new ones that you've seen. And okay, last concept. Um, this one's sort of all over the place, but this one's like completely new to Orgo 2. It is something that you've seen throughout the whole course, and um, it is practically very useful and gives you a lot of ways to go around reactions. So you can use protecting groups. All right. So you've learned some fair number of these. Okay. First one that you learned way, way long ago in the course is to use tips. And you just protect alcohols by using tip Cl. You could just add that, and there you go. They'll all just attach onto alcohols, and then you could do a whole bunch of stuff like use Grignards. And the nice thing is it's super easy to remove tips because you just give it like something with fluorine in it. And tips really loves to just grab onto fluorine, so it'll take that instead of the oxygen, and there you go. Right. But you also learned about acetals as another sort of protecting group. And in fact, you spent a whole chapter talking about acetals because you talked about sugars. So, like most sugars are normally hemiacetals, but you can also pretty easily just make them acetals instead, which would make them non-reducing sugars. And, you spent this whole chapter talking about it. You also talked about the other kind of big reason that the sugar chapter was also important is because you talked about like stereochemistry a good amount in sort of an actually interesting and more useful way than you saw stereochemistry in like Orgo 1. Um, but yeah, you talked about those here, which is kind of important. And you also use them in protein synthesis. So there was this sort of like method of protein synthesis where you had to protect one side of your amino acid in order to do reactions using the other side. Especially you have to protect like the amine, the NH2 of an amino acid, because that's the more reactive side. So you kind of have to take care of that first, and then from there you can go on to do protein synthesis, deprotect, add on a new amino acid, deprotect, and so on. Just to kind of like give another example of where you've seen something like this, there's also this sort of idea when you're doing substitutions on a ring. So you could take this like NH2 and then you can protect it in some sense. This isn't quite protection, but it's like sort of attaching a group and then deattaching it in order to be able to do a reaction. And then from here, you could do like, let's say some sort of Friedel-Crafts, right? That's probably the most common one that you dealt with. So you could do something like this, and you can use a Lewis acid now. And that will let you finally do stuff. Right? And then over here, you get this carbonyl. And then you can deprotect. Right? And this is an amide, so you can deprotect it without too much trouble. This is sort of another example of like where you saw this sort of strategy where you stick something onto your molecule with the intention that later you're going to remove it. But sticking that thing onto your molecule lets you do your chemistry, which is fairly important especially when you have some more complicated molecules like you want to do a Grignard on a molecule that has an alcohol. Well, you're going to need to use TIPCL, or maybe find some more complicated way around it, but that's a really effective way. Um, yeah, it's very useful. Okay. Those are sort of the big themes that I had to talk about. And in doing so, I think I've gone through and covered most of what you've actually talked about in the class, hopefully. So I will save, let me save this file. Please let me save. There we go. Um, week 12, the final week. And this is review 1. Okay. There we go. That's saved. And so from there, okay, we're just going to go through and do some broad problems that you've seen the ways to do through the class. So we'll just do some review. Let me this. I was looking into like different programs and things that I can use to do this. Um, because like, I was thinking how like, oh, like Khan Academy or whatever looks like their videos look so nice. You don't have all this like junk on the sides and everything. Um, long story short, I couldn't find anything, so I'm kind of sticking with this. But maybe if I think about it for much longer, maybe I'll find something new. But whatever. Okay, how about we do some chemistry? All right, here we go. We have all right. Predict the major products. Show stereochemistry where appropriate. Okay, this is your standard predict the product question. So over here we have sodium methoxide. Okay, we know that looks like this. And all right, I spent this whole time talking to you about carbonyl like substitution reactions. So all right, we'll go up here. Electrons will move up. They'll move back down. Okay, we'll kick off that ethoxide, and all right, well, we got the same thing. Okay, so presumably we're going for something a little bit more than that. So, does anybody have an idea of what we're trying to go for with this reaction otherwise? So, well, we're not attacking with the carbonyl. So what else can we do?
Could you do like a hydrolysis?
So what sort like hydrolyzing this whole thing, this ester?
Yeah, like taking the ester and the alcohol and acid. Well,
Okay,
not
so
acid,
if we
but
had like yeah, so if we had like water, it can go up here. Um, well, I guess in that case, well, I guess that would be if we had water around. But we are
yeah.
told that we're doing this in ethanol.
Mhm.
So let's say that we don't have water. Um, although, well, good thought. But in this case, because we only have this ethoxide, um, that would be just doing this and then we kick this off. So any other ideas about what we can do here?
Do you pull off the alpha hydrogen?
Yeah. Okay. So we can do that. And in particular, this is kind of nice because there's only one side to pull an alpha hydrogen off, right? We only have one of these, and there's only one place to pull an alpha hydrogen off. Okay, so now we have this minus charge here, and there's that ester. Okay, and well, there's no way there's enough room in this molecule to react with this minus charge. So what are we going to do instead?
Ketoenol tautomerization.
Uh, well, okay, so we could do that. Well, in this case, we've already got our enolate. But okay, so well, we could have this keto enol tautomerization, although that's not going to help us much because this O minus isn't very reactive. It's not going to do much. If we're going to react anywhere, it's going to be on that carbon, that really electron-rich carbon. So, what can that really electron-rich carbon attack? Any ideas? All right, well, there's a whole load of this stuff floating around, right? So why don't we just react it with that? Okay, let me get rid of these other arrows. So we have this enolate, and why won't it just react with another copy of itself? Maybe now not the enolate, but instead just the starting material. But okay, you make an enolate, and then it's going to go up here. All right, once we're up there, then this is something we've seen before, right? We're attacking with the nucleophile. All right, so we kick up, but this is an ester, so we kick back down and remove the ester. So what'll happen is we have this side that we started with. Okay. And then we've made a new bond onto this carbon. Let me use a different color. Oops. Okay, so this carbon will be red, and then we'll say that we've attacked onto this red carbon. All right, well, there's one carbon off to the side. We kicked off that ester, and we have that carbonyl that we regained. Okay, and then let me just redraw. Okay, so that's what our product can look like. Um, in particular, this is a beta keto ester. So what reaction did we just do? There's a name for it. So what did we do?
Malonic ester synthesis. No, acetoacetic.
So remember, so the malonic ester synthesis and acetoacetic acid synthesis, this is what you start with. You start with something like this. But in this case, we started off with this and we ended with a beta keto ester. Beta keto ester. That's so hard to say. So, any idea?
Was this a Michael edition?
Michael edition, we have to do. We have to attack onto something that's conjugated. So something that looks like this. So this is a Michael edition.
Is it a Claisen condensation?
There we go. Yes. So this is a Claisen condensation. Okay. So the thing to remember is Claisen condensations make these beta keto esters. Or maybe if that's not the way you like to think about it, because like I don't know, like you're not given the product, right? So you have to think about it a different way. Claisen condensations use um, they use these alpha carbons of esters in particular. Okay, if this wasn't an ester, this was just a regular ketone, then okay, this would just be some condensation reaction, whatever. Because this is an ester, we can kick it off at the end, and we get these two ketones, or this ketone plus this ester over here. That's what makes it a Claisen condensation. Um, that's kind of the idea. So here we're doing a reaction with esters in particular. So this is the sort of product that we get. That's what a Claisen condensation is. Okay. Any questions? This is like the over here. This is like the malonic acid, and then acetoacetic acid synthesis is like I think it's like this, but kind of specific. Let me go check. Yes, yeah. So we start with this for acetoacetic acid. Okay. And for Michael, the big idea with Michael additions is that we always use something that's conjugated. Okay. That's kind of the big important part. It actually doesn't have to be a carbonyl, or like it doesn't have to be a ketone. It can be like an amide, or I think it can be an acid. I think there's even some really crazy one where it's like you can use something like this because you can move the double bonds like that. But well, all right, maybe we won't worry about it too much. I don't think that's ever shown up before. Um, I asked once about it, and they were like, "Yeah, this isn't relevant." So this is the big idea with Michael additions. Remember, it has to be something that's like conjugated like this. So you don't attack onto the carbonyl, you attack like somewhere else, which moves up to the carbonyl. Right. Grab one. And oh, I should paste it in. Okay, here we go. So this one has to do with sugars, which, boy, these are fun. But it's okay. All right, there haven't been too many reactions with sugar, so well, let's see what we're dealing with. Okay, so step one, we put it in bromine water. Okay, so bromine water will oxidize. Those are oxidative conditions. Bromine, we don't think about it this way that often, but it is an oxidizing agent. So okay, we're oxidizing. Does anybody want to be brave and say what we're oxidizing?
Aldehyde?
Is it just the aldehyde?
Yes.
Yes, it is. There we go. Yeah. Wanted to see if you were on your toes. There we go. Okay. So it is just the aldehyde. And there's only one way to really oxidize an aldehyde, so we turn it into an acid. All right. There we go. So we have that. And now we have this very specific conditions, which is we use iron sulfate and hydrogen peroxide. So this is also a very particular type of reaction. Maybe I'll ask first. what do these conditions actually do to this molecule? Like what happens?
It's it's gonna shorten the chain. Um, it's the rough degradation.
There we go. Okay, you got both of my questions. So yes, this is the rough degradation. Okay. In fact, step one plus step two is the rough degradation, and then using this iron sulfate and hydrogen peroxide, that'll take off this CO2 at the top. Okay. So we shorten our chain by one, and instead it becomes this aldehyde. Okay. So now this carbon in red is the one at the top. Okay. And we lose off some CO2. All right. And now we have. How about actually let me put it down here. So we had methyl lithium, or yeah, sure, yeah, methyl lithium. Okay, so we had a whole bunch of it. Um, what is the first thing that the methyl lithium will do?
React with the alcohol groups.
Uh, okay, I think I heard you there. Yeah, so it'll take off the hydrogens from the alcohols. All right, so that is the first thing that will happen. That is kind of useless though. That doesn't really do anything for us. Okay. Now, what's the other thing that it'll actually do?
Open up the carbonyl.
Yeah. So from there, it'll go up into the carbonyl. Okay. So from there, we have more methyl lithium, and then we add acid. Okay. And so, all right. Well, at the end, all these alcohols get back. Okay. Not not crazy. And then we also we add a methyl there. Okay. And then at the end, oh, did I make a mistake? So should this I think should have been a carboxylic acid. If I'm not mistaken. Hopefully it was.
Is that
Because
because
that
of
would.
Sorry.
What's up?
Is that because of the H2O2, or is it just because? Why is it a carboxylic acid there? Sorry.
Yeah, so I think if I remember correctly, um, the rough degradation, like the product will have a carboxylic acid on the end. That would be because of the Oh no, it doesn't. No, okay. No, it doesn't. No, I had that wrong. I was looking at the answer and just to like double check and uh it had something different. But no, okay. All right. Anyway, no, we had it right. Um hydrogen peroxide's not I don't think it's a strong enough oxidizing agent to make this aldehyde go into a carboxylic acid. The product of the rough degradation is usually this aldehyde. So, okay, everything we did was fine. Um so I won't worry about it too much there. Okay, then we add this methyl lithium in. All right, so that'll attack onto the carbonyl, and then we protonate everything. Okay, so what we wind up having is, all right, these electrons get kicked up, and this this methyl minus goes into there. So, okay, we get a methyl, and then we get an OH here. Whoops. Yeah, there's no charge. There we go. And over here, there's no stereochemistry. Does anybody want to tell me why this carbon has no stereochem? It's racemic at that carbon, I should say. Maybe I was using my terms poorly. So like we get a 50-50 mixture of at this 50-50 mixture of stereochemistry at this particular carbon. This goes like way back. Does anybody want to remind me of why that happens?
The CH3 could attack from either side of the aldehyde.
Yeah, exactly. Here we have this aldehyde, and this methyl can come in from above, or it can come in from below. So we don't get any preferred stereochemistry here. Yeah, maybe you could say like something about like there is some chirality in here already, so maybe it wouldn't be like exactly 50-50, but there wouldn't be that much selection. Anyway, not the biggest thing in the world. We start with something. Yeah.
I have a question, sorry.
Yes.
What are the conditions for when you methylate the entire sugar? It's not excess MeLi then?
No. So here, this is like something that's really basic. So if we wanted to methylate the sugar, yeah, when I actually looked at this problem first, I was like, I just kind of was like running through it real quick, and then I was like, oh yeah, you methylate everything and then you're done. But no, not in this case. So methyl lithium is like really basic, so it'll take off all those acidic hydrogens. If we wanted to methylate all of the alcohols, then we would have, okay, we would take this aldehyde, right? Let's say we were over here, and then we had this sugar. Don't ask me the name of it because I won't be able to tell you. All right, so we have this sugar, and then if we want to methylate everything, then we need these OHs to act like a nucleophile. In other words, we need a really electrophilic methyl. So, best way to do that is, well, not lithium. I almost wrote that again. Is to use something like methyl iodide. Okay, that iodide will pop off really easily, and so if we have excess of that, then we'll get everything methylated.
Okay, yeah, that makes sense because I remember that, but it was different. Okay, thank you.
Yeah. No worries. I mean, I looked at this problem at first and I was like, yeah, this is nothing, right? You just methylate. No, it's not. You have this aldehyde, and this is an organometallic, right? So it'll attack an aldehyde, preferably. Yeah. So this is a solution that I think we should get. Yeah, I got tripped up with that rough degradation thing because this solution that I have says like, okay, it says that over here you have a carboxylic acid, not an aldehyde, and then from there you kick off that OH and you wind up getting a ketone here instead. But that's not right. Right. Here you have this. You make an aldehyde from the rough degradation, and there's nothing to oxidize that aldehyde into an acid. I mean, there's this hydrogen peroxide, but that's not going to do it. That's not strong enough. So yeah, this is what it should be. How about I pull the next problem? Here we go. Copy and paste. Oh, it's right there. That That is so convenient. Okay, I need my marker or my pen, I guess. I don't know. Okay, here we go. So we have this molecule over here that's kind of nice. This is a bit of a gentle molecule compared to the last two, right? This one's not too crazy. And so we have this amine and we have sodium triacetoxyborohydride. Okay? So as far as I can tell, there's only been one real reaction where you've seen sodium triacetoxyborohydride. Okay? So what type of reaction is that?
Reductive amination.
Yeah, there we go. Two of you got it at the same time. Okay, great. So we're going to be doing reductive amination. Okay? First step of reductive amination is going to be to form what?
Amine.
Exactly. So we form our imine, which will look something like this, which could have like a plus, right? Okay. And well, from there's not that much to think about, right? We just reduce. Oops, not aromatic. Always do that. And there we go. And that's it for this one. Nothing too crazy. Why did we have this? Why did we specify that it's acidic though? Maybe I should ask. This is a good question. If I may, you know, applaud my own question. So why was it acidic?
To stabilize the positive charge on the nitrogen in the intermediate.
So if you had it be okay, yeah. Well, if this was under basic conditions, then you couldn't have that positive charge, right? So that's true. It doesn't quite stabilize it though, but can we go from this carbonyl to this imine without it being acidic conditions?
Is it possible that the base could have attacked the carbonyl as well?
Okay, yeah. So you could have done that. If you had if you had like an OH minus, then it would attack like there, and then it would attack, then it would go back up, but it would kick off that OH in the end anyway. So the reason I was thinking, at least, is because in general, when you make an imine, it has to be under acidic conditions. So, imine formation needs some mild acid. Okay, so it was used for this first step. This is where we use the H+. And then in the second step, this is where we use this guy. Okay. That's what I was thinking. Well, you are right. Let's see, if this was basic, then it would be weird to have this positive charge. Because in general, whenever things are in basic solution, you only have neutral or negative. Okay. If there was something that was really basic, like an OH minus, then okay, it could attack at this carbonyl, but the carbonyl would just kick it back off. So this was the main reason that I was thinking. Although I do think both of those reasons that you guys gave contributes. So yeah, that's just something to remember about like when you do amine formation is that it needs to be slightly acidic. Right. Any other thoughts on this question, the previous ones? All right, here we go. Copy. And oh, it's not that far away again. Excellent. All right, here we go. Where's my pen? There it is. Okay, so here we go. All right, we have this amine, and I'm just gonna go ahead first step and put these dots here because, well, that's the real relevant part of most amines. All right, so here we go. We give it methyl iodide, and we give it excess of it. So, well, we already mentioned earlier that methyl iodide is super good at just methylating whatever it comes in contact with, right? So, how about I just tell you, all right, we're going to get this amine attacking here. We're going to kick off that iodide. So I'm going to rewrite this. This is a phenyl group, so I'm just going to rewrite it as that. And then we have this nitrogen. There's that other phenyl group we started with. Here's that. And now we have this methyl. And there's a plus there. All right. So now we add this silver oxide and water. All right, maybe this is starting to look familiar now. Does anybody want to say what reaction we're working with?
Hoffman.
Yeah. So this is a Hoffman elimination. Okay. All right, so this silver oxide and H2O is going to put some really strong base there. Right? And in the case of Hoffman elimination, what this does is it puts an OH minus somewhere there. Okay? So we have this OH minus. And the idea now is that we're going to eliminate something. So, okay, what hydrogens can we actually eliminate? There's that hydrogen. There's a hydrogen there. There's a hydrogen there. I should say, what hydrogens are there at all? Not all of these we can eliminate. Okay, so we have these 4 hydrogens. The rest are on the phenyl rings, or, they're equivalent to these, so, well, we're not going to worry about those. So here's 1, 2, 3, and 4. Okay, and, whoa, not that. All right, so here's the most important question. Which of these is that OH minus going to take off?
Number 4.
Okay, yeah. So it'll take off number 4. Although, well, let's think about it, and see what we can actually do. Okay. So, actually, how about let me really go wild here and use a bunch of different colors. Okay, so how about I use like green over here? Okay, so hydrogen number 1. Let's say that we go over here and we pull hydrogen number 1 off. Okay, well then these electrons will go here, but you're also trying to remove the nitrogen from the same carbon. That doesn't make a lot of sense, right? Like you have this one carbon and you're trying to pull 2 different things off of it at the same time. That's not really going to work. Okay, and then here's number 2. All right, well, oh man, I'm really reaching here. Okay, well, if we go around and try to take number 2 off, well, we're doing the same exact thing, right? We're trying to remove something from one carbon and then remove the nitrogen from the same carbon. You can't really pull 2 things off at the same time like that. That's a bit too much to ask for. And, oh, okay, here we go. Same thing with number 3. Okay. None of those 3 are going to work. But over here with number 4, if we come here, take off that hydrogen, the electrons are going to move to make a double bond there, and you can kick off that nitrogen without a problem. It looks just like normal E2. So, number 4 is the one that works. The rest of them don't. This wound up being more complicated looking than I would have liked. I also chose the wrong colors, right? Red normally means bad, and green is good, but... Oops, okay. Anyway, so we kick off this thing with 2 hydrogens and a double bond. So we have that as one product. Okay, and then otherwise that nitrogen, everything else stays the same. Okay, so we keep the thing over here that we didn't remove. We keep that methyl, which we also didn't remove. We keep that phenyl, which we couldn't remove. We didn't even think about removing that phenyl. And we also got this this little guy over here with the 2 carbons and the double bond. So there was our whole product. That's it. This is the Hofmann elimination. This is kind of one of the few reactions that you can do with amines. Like you can do a lot of reactions with amines, but this is one of the amine specific non SN2 type of reaction that you could do with them. Okay. The other one being the cope elimination. That's kind of the other thing you can do. Right. Well, let me pull another one. Oh boy, this one looks kind of complicated. I didn't look over the problem too much before. We're doing this. I have a rough idea of what we're supposed to do, but okay. All right. Whatever. Here we go. We have. Okay, I got plenty of room. Let me get my marker, and I'll leave it real big. Okay, we start off with pyridine. I don't know what that is, so I Googled it, and then, well, it's just that. Okay, it's a 5-membered ring. One of those things is a nitrogen. Okay, so you've seen this plenty of times. You just might have not known the name for it. Okay, so first step, we put in this, and we put it in kind of acidic conditions. Okay, so what are we going to make here? What are we making?
An imine?
Okay, yeah. So we are making an imine. Okay, which is good, because that's what we did before. All right, but you could do something with this to make it a little bit better. Okay? In the same way that you have like keto-enol tautomerization, what can you do with this molecule to kind of make it a little bit more familiar?
Is this like the Stork reaction? Where you...
Yeah.
Okay.
Well, okay, yes. So in the Stork reaction, what do we...
You take off the H and then like move the double bond N up, like in an elimination.
Yeah. Yes. So, okay, so we can move this up, and then we take off one of these 2 hydrogens. Let me write these out. So we can take off this hydrogen or this hydrogen. Okay. So we can take off 1 or 2. So which one are we gonna take off? Any thoughts?
Would you take off number 1?
Okay, what makes you say 1?
Because you get a more substituted double bond.
Oh, okay, yeah. So this can kind of go back and forth. This is sort of like the same way as you would do keto-enol, but except, it's slightly different now. And we can get this over here, this double bond. Okay. And your reasoning for it is that the double bond is more substituted, which probably good. Yeah. I think that will work. I haven't thought through which of the two it'll be, but my first thought was you're putting a whole bunch of electron density onto either this carbon or this carbon over here. So my thought was, which of these two can hold like a lot of electron, or can hold more electron density? Which one of the two is more stable, having more electrons on it? So my my thought regarding that was that we would put it on 2, because you could sort of think about it like putting a negative charge onto onto something. It's not quite like that, but most of the electron density is located on that carbon. So I was thinking about it as which of these two can hold like a negative charge better. So I was thinking it would be the other one, but I'm open to ideas about it. Let's see. Have an enamine. Their particular preference. I don't know. How about we try it and we see what happens. Yeah. Does anybody else wanna weigh in here? Yeah. I think thinking about it more, I think it would wind up being more on this other carbon, because you have the sort of thing where like you're loading electron density onto one of the carbons, and that's sort of what'll drive the stability of it. Is where you can put more electron density. So I think you can put it more on the other one, which would mean that you'd get the double bond on the other side. Yeah. And then yeah, so you would get you can choose 2 because it more stably holds stably. I don't know if that's entirely a word. More stably holds the electron density. The other thing to sort of think about is that like this isn't it's not so much this molecule or this molecule. I don't want to, well, it kind of is, but like in some sense it's a little bit like resonance, where you can go back and forth between these, right? They're all in equilibrium. So it matters especially how much you have of this one with the double bond on the right, and how much you have of the other one with the double bond on the left. Um, yeah, and I think this one winds up being more stable because of that whole electron density thing. I guess this is a weird situation because like you kind of have to compare this double bond stability to the stability of like having those electrons there. Um, but it should wind up being this with the electron density on the right. Okay. Yeah. I didn't think about this one too much beforehand, so I don't have like the best way of explaining it. Sort of besides that, right? Like here you have these three carbon substituents. So if you load it, like there's already a whole bunch of like these big bonds right there. So if you tried pushing more electrons onto it, you'd kind of be like pushing electrons where there's already a lot of them. But if you put it over here on the right, then you have these two hydrogens, uh, or at least normally, or I guess in this state you have that like one hydrogen that's hanging there, and that's not as big. That's not like pushing as much electrons into here, so you can kind of there's more space for these electrons to fill. Okay, so my kind of poor explanation aside, um, so we're working with this enamine. This is a Stork reaction. So okay, good. We've got that going for us, right? And now we add this methyl vinyl ketone. Okay, and I could never remember what this one looks like, but there's a methyl, there's a vinyl, and there's a ketone. So okay, it looks like this. I guess it's in the name. I've never thought about it too much. Okay, now we have this. Okay, and methyl vinyl ketone is going to let us do what reaction?
Michael addition.
Okay, yeah. Now this is going to be a Michael addition. Okay, so here we go. We move everything up. So here's this structure. So we have this tertiary amine, and now over here we have. Let's see. Let me number carbons to make things really a little bit clearer, both for myself and for you. So 1, 2, 3, 4. So okay, over here we have 1, 2, and then 3 and 4. Okay, so here's 3 and 4. 4 we didn't even bother. We moved the double bond to be between 2 and 3, and now we have this O minus over here. Okay. This is an enolate, so okay, that's not a lot of trouble. We can just turn that into a ketone. There we go. Okay. Normally I'd be going up, but okay, there's still a good amount more to do here. So this, let's say, okay, over here we had step 1. Over here we had step 2. Let's do step 3 now. Now we're adding LDA. Whoops. And we're heating this a whole bunch. Okay, so let's see. We have this this structure over here. We're done with our enamine because now, we've actually used up that double bond now. Now it's just a plain old tertiary amine. Not much else going on there. Okay. We do have this ketone though. And okay, we can work with this ketone instead now. So, oh wait, no, I totally messed that up, right? So whenever you use an enamine, these electrons push back down. So I should say that is actually an imine. There. Okay. Well, now we have this LDA, so we can pluck a hydrogen off of somewhere. Okay. Uh, Maybe let me draw this structure a whole lot bigger so we can see what we're working with. Let me get a big eraser. Here we go. Let's see. Oh, I've done this before, but let's see if it'll work again. Here we go. Let's make this much larger. That's a little bit ugly, but we're not going to worry too much about that. So I want this. Oh no, it's not letting me draw now. Okay, all right. Let me go backwards then. I flew too close to the sun with my Photoshop abilities. So I'll just redraw it. So okay, we did this keto enol tautomerization. This is just keto enol now. So we'll keep this imine. That'll just stay. All right, so let's see where we have hydrogens. We've got a hydrogen here. We've got one over here. And let's see, are we able to actually to take anything off of where this imine is? Well, normally this enamine will form in acid. Right, over here earlier we formed it in acid. So in this case, let's see, can we? I don't entirely think so. Also, I should say this carbonyl is like more withdrawing than this imine is. So we'd be more likely to pull off the carbonyl anyway. So okay, all right, here we go. So we've got hydrogens 1 and 2. Any thoughts on which of the two of these we're going to pull off?
Yeah.
2. Okay. So why 2?
Is that just because it makes a more stable ring when it closes?
Yeah, okay. So you know where this is going. So we pull off 2 because when we get a minus charge over here, it's going to attack at that imine. And okay, we'll get rid of that whole imine situation. We'll get rid of the whole amine. And at the end, we'll just have we will get a ring. Yeah, so at the end, we're going to get a ring. Okay. So this thing will take LDA, which is step 3. Oops, here we go. All right, so step 3, we got LDA in there. So there's our imine, and here's our enolate. So okay, now this enolate is gonna go after this imine, and then from there, okay, so we have now this amine that's hanging off, and we've made. Oh, we definitely need to count carbons here. So 1, 2, 3, 4, 5, and 6. Okay, so it's going to make a 6-membered ring. That's exactly what we wanted. Okay, so let me just draw that. And then this carbonyl is on number 5. Okay. And, well, we're going to get rid of this amine because it's kind of just hanging off there. So, okay. Let's see, we have a hydrogen that's over here. And I guess there's also this hydrogen that's over here. So, let's see, what do we have? So we have LDA and heat. I guess normally when you heat something like this, right? This is like analogous to a Robinson annulation, isn't it? Because we've done this this Michael addition, and then from there we've added we did like one of these alpha substitutions, okay, and we made a ring. So this is sort of your Robinson annulation. And then when you do a Robinson annulation and you heat it a whole bunch, then you also wind up kicking off this this extra thing that's on the end. Okay? So we're going to heat it a whole bunch and kick off the amine. Okay? And oh, here we go. Now I've yeah. I know now I know what question to ask you too. So we have once again we have these two hydrogens. We have 1 and 2. So now this time I'll ask, which of these two hydrogens are we going to pull off?
Two.
Number 2. Okay, and why number 2?
You get like conjugation.
Okay. Yeah, okay. So we get something that's conjugated like that. Okay. Yeah, so we actually get this conjugate ketone. Yeah, that's good. Well, at first I was thinking you'd pull off 1 because you get a more substituted double bond, but no, you also get the same substituted double bond here. Let's see. Yeah. Oh yeah, plus there's that rule about like bridged bicyclic systems or something, right? This is technically one of those, I think. There's like Brett's rule. Okay, yeah. So I think yeah, it should be number 2. Um, I think this whole Brett's rule thing also applies, but whatever. Yeah. So we pull off number 2. They're equally substituted. You get this conjugation also, which is like extra nice. Okay. And all right, final step. Here we go. We add in a cuprate, and then we do acid workup. What is going on with this cuprate? So if we add this cuprate, what's gonna happen? What's it gonna do?
It's gonna open up the carbonyl and add a ethyl group.
Okay. That is a good idea, but these reagents normally aren't strong enough to push up a carbonyl and just like totally open it.
And Gilman reagents also do Michael addition.
Yeah. So these are also good Michael donors. Okay. So we can actually push up here and do a Michael addition. Okay. And so if we're doing this Michael addition, from there, the thing we'll wind up with at the end is that ethyl there, and then we'll get this ketone. Okay. Oh wait, oh, was my ketone in the wrong spot? Oh yeah, it totally was. Look, I counted carbons here and then I like completely misplaced my ketone. Oh, and okay, whoops, I'm so sorry. That actually affects like some of the other stuff we do. So, okay, I should have thought about that a bit more carefully. How about we do a bit of erasing? Okay, so well, we know what's gonna happen. That's kind of the important part, right? We know that we're gonna make a double bond and we're gonna do a Michael addition. Okay, so we have this over here, and there's this nitrogen. So we're gonna remove this hydrogen here because okay, it'll make a conjugated ketone. There we go. Okay, that's better. Now we could do just our Michael addition. Whoops, I can't believe I missed that. Even though I said like, oh yeah, we count carbons. Um, okay, here we go. Well, if anything, that should be evidence that counting carbons and actually doing it mindfully is quite important. So from there, we do our Michael addition, and we wind up with that as the final product. This is a Michael addition. Okay, and it looks like that. Yeah, and okay, so this is what we should get at the end. A very complicated route to get there, but looking at it kind of like big picture, what we did is we formed this enamine, so this like thing to do a Stork reaction. Although we used it to do this like this Michael addition, right? Enamines are pretty good for doing Michael additions, so we used that to do a Michael addition here. And then from there we did this we took off that hydrogen and we made a ring. So this is like a Robinson annulation, right? We did a Michael addition and then we made a ring. And you know, we did the extra step of a Robinson annulation where we heated and we kicked off that amine that was there. Normally that would be like an alcohol that's there, but we kicked it off as an amine. And then lastly, we did a Michael addition on the final product that we got from a Robinson annulation. All right, let me open up a new document, a new image, I guess. They aren't quite documents. Okay, here we go. So next question is, this is like truly everybody's favorite. I guess these can't really show up so much as multiple choice questions, but these are still like some of the best practice that you can get is to do synthesis problems. So, all right, well, we're gonna do them. Here we go. Okay. So our final product is this. It has this thing, which like we have not seen very much. We truly haven't dealt with a lot of this stuff, but it's got this C double bond N. Okay. So this might remind you of like, okay, this kind of looks like an imine, right? So what if we started with a carbonyl here, and then we went up by adding like NH2OH. Let's say that we have that because, well, it exists. It's just like a slightly unusual reagent, and okay, it can be slightly acidic. Okay. So now that we've used retrosynthetic analysis for like figure out what the last step was, now this is kind of just like a more normal problem, right? We want to go from this benzaldehyde to this thing over here. Okay? This is now a bit more approachable. So, well, okay, what thoughts do people have about this? How can we do that?
Can we do acid halogenation? Oh wait, no, we don't have a carbon.
Yep, no extra carbons up here.
Could you do a Grignard and then oxidize it again?
Yeah, I think you can. So here we go. We attach these 3 carbons, right? So how about we just do? You could use a Grignard. Why don't I just use lithium? Okay. So we could just add a whole bunch of that, and then followed by a workup, and then from there oxidize it into a ketone. Okay, so pick your favorite oxidation. Swern. Swern is really nice, right? There we go. And you get your final product. Okay. So this is like the nice way of doing it. This is the not crazy way. I was looking at the solutions earlier, just to check, like, yeah, this is really it, right? And then the solution for this is way crazier. So how about I show it to you just quickly, and well, you won't have to worry about it too much. Okay. So the solution is you start with this. So like the solution that I have like in my key, but this is not. I wouldn't worry about it way too much. So okay, you can start with this, and it's slightly acidic. So you form what looks kind of like a what is it called? An acetal. Okay, this looks just like an acetal, except it's sulfurs instead. But the neat thing about this sort of structure is that now you've done what's called switching the polarity of this carbon. Okay, so earlier this carbon was really positive. Okay, like there's no way on Earth you could remove this hydrogen. That would be crazy. And now, well, I guess this is still positive here, but the idea is you can remove this hydrogen once you have this here, okay? Because these sulfurs will stabilize it enough. So from there, you can do like, you could deprotonate it somehow using some like pretty strong base, okay? So use like butyl lithium. It's a good base, right? It's a very strong base and it'll pull that hydrogen off. So from there, you get something that looks like this. All right, and now this is a nucleophile. So now you can attack, like, let's say, something that looks like this structure. And oh wait, oops. So this is a really good nucleophile, and what happens is you can give it something that looks like this, and it'll remove. No, that's still not right. Let's see. So, okay, well, you can kick off that bromine and through okay, well, the important point is I think you wind up kicking off that thing. So now you get something that looks like this, and from there you can do some stuff to turn this into, I think, a ketone, and then you can go up to here. Okay. As you could tell, I didn't look into this method too much because this is like substantially more complicated than anything you would think about, or like I would think about either. Um, yeah, this relies on this sort of principle. I don't know if he talked about this too much in class, but I know when I took the course, he mentioned this sort of pathway, like very quickly. He talked about it with like the syntheses that he does in his lab or something. I don't know if he mentioned it in class, but like you totally don't need to do this. Uh, I wanted to mention it because like so you could see this is something that's out there, and like you know earlier when I was prepping, I like noticed this and I looked it up and I thought like, oh, this is kind of cool. Maybe I'll say something about it. You don't need to worry about it. All right, how about I follow up the next question? Okay. Where's my mouse? There it is. Okay. Oftentimes this sort of like sulfur thing and like using it to pull off a hydrogen, it's this strategy for synthesis called like Oompalong or something. That sound familiar? Maybe he mentioned it. Probably not. He probably didn't mention it, so yeah, that's totally fine. It doesn't matter that much. Okay. Um, Here we go. So we have this final product, and it's got an N3 on the end. So how do we always put an N3 on an azide? We really only know one way of putting it on.
SN2.
Yeah, okay. So it's gonna be by SN2. Okay, so it's gonna be doing some sort of SN2 reaction. Oops. L. Some leaving group. Okay. Although maybe we should have taken a step back first and thought about what the orientation between these two is. So here we have this chlorine, and it's meta to what we have over here. Okay? So that means we need a withdrawing group here. We need to add this chlorine, and then we can do stuff over here. Okay? So we need one withdrawing group. Okay, which will look like this, most likely. Just because this is a good choice that we can put on really easily. So it'll probably be like this. Then 2, we need to add the chlorine. And then 3, we can change the C double bond O to the single bond N3. Okay. That's the method we're gonna have to take. Well, that's okay, right? We that's how we started retrosynthetically already, so we can work with that. But since we thought about it, we can also just go forward. Okay? We can do this reaction where we add this like thing with the carbonyl. Okay? Which is called our Friedel-Crafts acylation in this case. Now we're adding our chlorine. Does anybody remember what the conditions for adding chlorine are?
Cl2 and AlCl3.
Okay, so it's just Cl2, AlCl3. Yeah, sounds right to me. So there we go. Okay, now we need to make this ketone into a leaving group with a single bond. So there are a million ways you could do this at this point. Does anybody have a good idea? Well, for one, we're going to have to turn this ketone into a single bond, right? So why don't we start with reduction? Okay. I'll give you that much of a hint. And then how can we turn that alcohol into a good leaving group?
Tosyl chloride?
Yeah, sure. Tosyl chloride. That's a good one. That's actually a great one. I'm a big fan of tosyl chloride. Okay. Any other thoughts? How else could we turn it into a good leaving group?
PBr3.
Yeah, there we go. Yeah, PBr3. If you really want to go wild, you could do like phosphorus and iodine, which will make it into an iodide instead, an I here, and that's like a crazy good leaving group. But there's no need, right? Remember, this is a benzylic substituent, so it'll undergo SN2 or SN1 really like without much problem. So whatever we use, it's going to be okay. It'll work pretty well. This N3 is also like a really good nucleophile, so all right, this whole reaction is pretty much just in our favor. Okay. We've got only two more. Two more problems left. Here we go. And it's right down here. Perfect. Oh, man. Oh, what do we have going on? Okay. Let's see. Okay, there's quite a lot going on in this problem. This I will tell you right away, this is not a very fast synthesis. Okay. So let's see. Does anybody have any thoughts how we might even start with this problem?
The CN's got to go, right?
That's right.
Yeah.
It does. Well, so what can we do with it? Let's see. We can. Where's my mouse? There it is. Okay. We're gonna have to do something to get rid of it. So we could do like, let's say, hydrolysis. Okay. So we know we can do hydrolysis, right? And that will get us, instead of that CN, what, an acid, right? That should wind up getting us an acid, I think. Yeah. Well, we need this N in the final product, so or just hydrolysis might give us an amide. Well, okay, how else can we look at this problem? So over here we've got this tertiary amine. So
Can't you make the CN into a NH2? Wasn't there like POCl3 or something that we used?
when you use POCl2, you're going from an amide to a nitrile.
Oh.
POCl3. Yeah. So this is a dehydration reaction. So here you're pulling an oxygen and two hydrogens off from the amide, and you're going to a nitrile.
Mhm.
In that case, that's not going to help us too much, but it's a good thought. Um, okay, here we go. So how about we do? Let's see. I'm just trying to think what the nitrile hydrolysis is like. What it gets you, right? It gets you a an amide. Yeah, okay. So this will get us an amide. Sure. That's a start, right? Now we've got some more stuff to work with here, at least.
Wait, I think nitrile hydrolysis was correct the first time. I think it gets you the carboxylic acid. Unless I
Okay.
could be wrong.
Yeah, I'm checking the book. It says if you hydrolyze it like a little bit, you get an amide, but then if you go like a lot more, then you get it to an acid. Um, yeah. So okay. Well, we've got an amide, so okay, that's a start. You know, we're working with something now. Um, from there, what can we do?
Can you,
Hmm.
instead of doing the hydrolysis, could you turn, like still going with the idea of turning the nitrile into an amine with LiAlH4 and then turning it into an imine and then attacking it with the two alkyl groups?
Okay. So you're saying that we can go like we turn it into this. That's so we can use like LiLH4, and then from there we can make it an imine. Mm,
What if we get rid of the CN altogether, like as a leaving group, and come in with excess NH3?
yeah.
So
So
that way we
that would
don't
be
have an extra carbon in the middle coming off
that
the
would be
ring.
really nice. But I don't know if we can really get rid of that CN very well. It won't come off by SN2 very easily.
I have an idea. Could we stick with the carboxylic acid and then reduce it with LiAlH4, and then heat that so it forms a double bond?
All right,
And
so let's
then,
see.
okay,
You
yeah.
said the carboxylic acid,
Uh-huh.
then LiLH4.
And then you'll form the alcohol
Yeah.
and then heat
Come
it
on
so
board.
you get a double bond, and then do ozonolysis to get a double bonded O, or a carbonyl group. And then I just added the amine with the two alkyl groups coming off of it.
I am totally on board with your way of doing this.
Okay, great.
Yeah. So I'll try to write everything and catch up here because there was a whole bunch. So you do ozonolysis and then you get this here. Okay. So well now we've gotten from here going up to this top is not as bad. Um, because now we could do like we could add ammonia and do reductive amination, or if we don't even want to put that much work in, well, we can add this and then one of those nice reducing things. Okay, and that's just reductive amination, so that'll do it. Okay, so what we did is we hydrolyze that nitrile to get an acid,